There is a place in the universe where almost nothing exists. Not a small nothing. Not the quiet emptiness between stars. A nothing so vast that if you placed our entire Milky Way at one edge and began traveling toward the other side at the speed of light, you would still be crossing it 200 million years from now. That place is real. It has a name, and it challenges one of the most basic assumptions cosmology makes about how the universe is supposed to be arranged. The structure in question is the Boötes Void, sometimes called the Great Nothing. It sits roughly 700 million light-years from Earth, in the direction of the constellation Boötes. Its radius measures approximately 62 megaparsecs, which translates to nearly 200 million light-years. To call it large undersells the problem. It is one of the largest known voids in the observable universe, and its existence forces a quiet but persistent question. How does a universe that began nearly uniform produce an emptiness this extreme? Astronomer Robert Kirshner discovered it in 1981, not by pointing a telescope at empty space and seeing nothing, but by doing the opposite. He and colleagues were conducting a systematic survey of galactic redshifts, mapping the large-scale structure of the universe by cataloging where galaxies actually are. What they found in Boötes was an absence. Where the survey expected to find roughly 2,000 galaxies distributed across that volume of space, consistent with the average density of the universe around it, they found 60. 60 galaxies where 2,000 should be. That is the observation. The deficit is not ambiguous or borderline. It is stark enough that the region earned a colloquial name on the strength of the data alone. To understand why that number is so surprising, consider what the standard cosmological model predicts about large-scale structure. The universe we observe today grew from initial conditions that were extraordinarily smooth. Small quantum fluctuations in the very early universe seeded slight anisotropies in the distribution of matter. Over billions of years, gravity amplified those anisotropies. Regions of slightly higher density attracted more matter, collapsed faster, and eventually formed the filaments, walls, and galaxy clusters that make up what cosmologists call the cosmic web. Regions of slightly lower density lost matter to their denser neighbors, hollowing out into voids. This process is well understood in broad terms and well supported by observation. The cosmic web is real. Voids are a natural and expected feature of it. Typical voids have diameters of 10 to 100 megaparsecs, between 30 and 300 million light-years. They exist because gravitational instability, working over cosmic time from those initial quantum seeds, produced a foam-like architecture of dense structure surrounding emptier regions. But the Boötes Void, with a radius of 62 megaparsecs, sits at the very upper boundary of what models of structure formation comfortably accommodate. Its sheer scale is what makes it cosmologically interesting. The formation of voids is inhibited in high-density environments and amplified in low-density ones, but even under favorable conditions, growing a single coherent void to this size within the age of the universe requires the starting conditions and the elapsed time to cooperate precisely. Whether the Boötes Void strains those conditions or merely tests their upper range is a question the evidence has not fully closed. The instrument and method that confirmed its structure were fundamentally redshift surveys. By measuring the redshift of light from thousands of galaxies, astronomers can convert those redshifts into distances and construct three-dimensional maps of galaxy distribution. The void in Boötes showed up as a coherent, roughly spherical underdensity in those maps. It is not an artifact of survey incompleteness in a single direction. Subsequent surveys refined its boundaries and confirmed the deficit. The Hercules superclusters form part of its near edge, which means the void has identifiable walls of denser structure bracketing it. The limits of what we know, however, are real and worth naming. Redshift surveys map the luminous matter we can detect. They are sensitive to the galaxies bright enough and close enough to appear in the catalog. Very faint galaxies, dwarf galaxies, or hypothetical dark matter-dominated structures without significant stellar populations could be present inside the void without appearing in the survey. The claim is not that the void contains nothing at all. The cosmological understanding of voids confirms that even the emptiest regions contain more than roughly 15% of the average matter density of the universe. What the Boötes Void lacks is the rich clustering of galaxies that fills comparable volumes elsewhere. That distinction matters for interpreting what the void means. 3 explanations exist for a void this large, ranked by how well each aligns with available evidence. The leading explanation is statistical within standard cosmology. The Boötes Void is an extreme but not necessarily impossible outcome of the same gravitational instability that formed all large-scale structure. On this view, the universe is large enough that rare configurations occur, and the Boötes Void may simply be one of them. This explanation has the advantage of requiring no new physics. Its weakness is that quantifying exactly how probable such a void is under the standard model depends on assumptions about the initial power spectrum of density fluctuations, and that calculation carries meaningful uncertainty. A second, complementary explanation invokes the role of dark energy. Voids are physically significant in this context because they provide evidence for dark energy through a mechanism called the Sachs-Wolfe effect. As photons of the cosmic microwave background travel through large voids, the expansion of the universe changes the depth of the gravitational well they traverse, producing a slight temperature shift in the CMB. In a dark energy-dominated universe, this effect is detectable. The existence of supervoids like Boötes is therefore not just a curiosity about where galaxies are absent. It is evidence woven into the large-scale argument for dark energy itself. This connection is well supported at the level of cosmological consensus, though applying it specifically to the Boötes Void requires careful CMB correlation work. A third explanation, more speculative and less supported, invokes physics beyond the standard model. Cosmologist Laura Mersini-Houghton published a series of papers between 2004 and 2006 arguing that the universe emerged from a multiverse landscape, and she made a set of testable predictions from that framework. One of those predictions was the existence of large voids, of the kind the giant void and structures like Boötes represent. The giant void, a second confirmed supervoid in the constellation Canes Venatici discovered in 1988, with an estimated diameter of 300 to 400 megaparsecs, was cited in connection with these predictions. This hypothesis is notable for being explicitly falsifiable in principle, but it remains a theoretical framework without the independent lines of evidence needed to elevate it above speculation. It is mentioned here because it represents a live scientific proposal, not because the evidence favors it over standard cosmological formation. The best current explanation, held at the level of working hypothesis rather than settled consensus, is that the Boötes Void formed through the ordinary mechanics of gravitational structure formation, amplified by the dark energy-driven expansion of the universe, and that its size, while extreme, is not necessarily fatal to the standard cosmological model. What keeps the question open is the absence of a precise probability estimate that the community has converged on. The void is large enough that some researchers have described it as uncomfortable for standard models, while others treat it as within the expected tail of the distribution. That disagreement is honest and unresolved. The decisive future test is more precise CMB mapping correlated against the three-dimensional structure of the void. If the Sachs-Wolfe signal from the Boötes region matches the prediction from its measured underdensity, that strengthens the dark energy plus standard formation explanation. If the signal is anomalously large or small, it weakens that explanation and creates pressure for something else. Deeper redshift surveys that probe for faint galaxies inside the void would also sharpen the measurement of just how empty it actually is, which directly constrains the formation models. What the Boötes Void ultimately changes is our intuition about uniformity. The universe looks smooth when you average over the largest scales, but the averaging conceals real structure, and that structure includes regions hundreds of millions of light-years across, where the cosmic web essentially failed to show up. The void is not a threat in any immediate sense. It is not approaching. It is not consuming anything. What it does instead is sit quietly in the direction of Boötes, 700 million light-years away, and refuse to be explained away cheaply. 60 galaxies where 2,000 should be. The number is 40 years old now. It has survived every subsequent survey. And the question it poses about how extreme the universe's large-scale architecture is allowed to be remains one of the cleanest tests of whether our best cosmological model is complete or merely good. If voids this large exist at the edges of what standard formation can produce, the question that follows is whether anything even larger waits at distances our current surveys cannot yet reach. That is not speculation. It is the next measurement.